So this Ferris wheel, rotating at a constant speed, makes one complete revolution every 20 seconds. So these problem lectures, which we're going to do, well, I think we'll end up doing this every week, almost every week. Oh, and by the way, you don't have any tests in week 7 and 8. We'll pick up with that again week 9 or so. So there's multiple kinds of breaks coming your way. There's a lot of ways to approach problem solving, and I'm going to try to model at least 2 different ways to break a problem down. And one of the ways to break the problem down is when you get to something that has information, you make note of it, and I'm going to quite literally highlight it in this case. And you say, okay, what can I do with that information? All right. And here's something that we can do. And so if you were to go back to the end of chapter 4 in my textbook, I don't remember which chapter it is in the OpenStax, but it talks about circular motion. And so we're going to bring force and circular motion together. The reason why I'm doing force and circular first is we sort of left the mathematics of circular motion alone at the end of the projectile motion, or the two-dimensional motion. We spent a lot of time on projectile motion because it's a little bit harder, but circular motion is also two-dimensional motion, just like projectile motion is 2D or 3D, depending on what you look at. So what can I do with this piece of information? Well, the angular speed, so instead of v, it's omega. So funny looking Greek W, that's my best attempt at that, will always be, at least in circular terms, this would be a way to define angular speed. It's 2 pi, which is one complete revolution. And then we like to use capital T for period, or the time that it takes to do one complete revolution. So this is a standard issue in not only the math textbooks you've endured in the past, but in my textbook and every physics textbook. We bank on people knowing that. Well, I know that in this yellow highlighted thing, we have 20 seconds as that. So it took every one revolution, which is 2 pi in radian terms. And so if you do the math here, we get 0.314, which is basically 2 pi over 20 is pi over 10, or a tenth of pi. 3.14 gets brought down. So the angular speed of this Ferris wheel is 0.3 radians per second. So radians, I could convert radians to degrees. If you multiplied it by 180 over pi, you'd get how many degrees per second. But in these computations, we need to, when we deal with angular quantities, we need to deal with radians, okay? And so that may or may not present an issue in your calculator, and I'll try to alert you to that when it happens. But the angular speed is 0.314 radians per second, and I'll show shortly how you can convert that to, maybe not in this problem, to revolutions per minute, but it shows up in other questions that way. So here, I just generated a new piece of information from the givens, and this is something that is a good scientific approach, is if you're able to generate new information from what you have, you should do it. Because what it does is it starts to quantify, it starts to pin down facts. And the more facts you have, the clearer the picture becomes. Okay? We haven't even got to what the question is about, and that's fine. We could just say, I don't know, that's an easy kill, I'm just going to do the math. Poof, I got a new piece of information. I know that it's going roundy-roundy at this speed, at least in radians. we're not using the radius of the thing yet, but we could. We're like, so omega, or angular velocity, is giving me a roundy speed, if you will, or circular speed. Angular speed would be the correct jargon for that. And I wonder, in an instant, or perpendicular to that circle, what would be the linear speed? Well, we had a formula for that too. Velocity, v, meaning the straight linear thing that we're used to, is equal to omega r. You took notes on this in this course and others. And so, omega, we just did that one. I'm going to leave the units off just for simplicity. And it was 25 meters. And so basically, that many radians per second times 25 meters, if I do the math, I get 7.85 meters per second. So that Ferris wheel's moving pretty good. And so that's the speed, if you could snapshot the speed tangent to the circular path, that's what it's doing. So at that point, if we put a vector arrow on it, if we made a simulation, it would have a length that was indicative of 7.8-ish, all right? So again, 2 pieces of information. They're easy pieces of information to generate, so you'll need to be familiar with those equations. And so other thing about this lecture, which will probably, I don't know how far we'll get today into it. We'll continue with these over the next few weeks. There's 3 main handouts we're going to deal with. This one, force and circular motion, then there's one that's just basically forces, and then conservation of energy and momentum. So we're going to be going through lots of problems, and the way these handouts are going to work is every now and then I'm going to skip a problem or two. Guess what's going to be on the test? The ones I skip. And I'm skipping ones that require you to do the stuff that preceded it. And so that should be a fairly decent way to move forward. But more on that later, but we're not having a test for a few weeks. All right, so we have 2 new pieces of information right off the bat from just those 2 sentences there. Okay, so could I get more? But wait, there's more. Yes, since we're in this angular circular motion world, there was this other thing, and this is the bread and butter of this particular topic, circular forces and circular motion. The A in F equals ma in Newton's second law, if you're dealing with circular motion, it must be centripetal acceleration. So this was in videos, it was in reading, may or may not have been in your trig or pre-calc class. Forget whether it is or not. But I developed it in the notes. I think you've been forced to go along with that. But here is the structure of centripetal acceleration. So centripetal acceleration, should have brought something better, but here's my ID card on a lanyard. And so, if I were to swing it around my head, or above my head, hopefully not into my head because I've cut myself. So why does the card have circular motion? Or I could do it this way, and that card is going in a circular path. Well, it's because this string, there's tension in the string, and it's keeping it, it's pulling it on that circular path. And so I'm providing a force, but it's not letting that thing leave the circular path. It's maintaining. If this is staying at that radius, there must be a force causing it to stay at that radius. That force is bottled up in the tension of this string, if you will. And if that's true, then it must be constantly accelerating towards the center. So that was the whole point of those lectures. Centripetal acceleration is a center-seeking acceleration that maintains the radius in the formula. And this is part of the thinking that usually escapes the thinker when they're first introduced to this kind of stuff is, what is this formula saying? And so what this formula is saying is that the centripetal acceleration, the center-seeking acceleration, or there's a force that's a center-seeking force, is keeping something on the center of what? The center of a circular path. And that circular path, if you think back to our circle lab, what's it defined by? Well, a radius. Radius is one way to talk about the center of a circle. The center of a circle is always connected to the radius, and that radius doesn't change, and that's why it's circular, is there's a constant radius. So that's a way to think about this formula, is there's an acceleration which is necessarily associated with some sort of linear speed, but the linear speed gets squared, whatever it means to square speed, and per radius, per this thing that's not changing. All right? So that's the conceptual view, if you will. And if we plug and chug the numbers, square 7.85, divide by the 25, we'll get 2.47 meters per second squared, which could also be meters per second, but I'll go with what's typical in the books and whatnot. So right off the bat, 3 new pieces of information are generated from 2 sentences and 2 pieces of information. And that's just saying, all right, it's roundy stuff. What goes with roundy stuff? Omega, centripetal acceleration. Can I compute them? Oh, yes, I can. Yay. So now I have new information. All right. Ultimately, what we really need from this new information is just the last thing we did, because what's coming next here is an indication that we're dealing with forces, assuming we didn't know that it was all about forces to begin with. So the question, to kill time, you decide, calculate the total force. Oops, switch to highlighter. This is the goal of the problem, all right? So that's what we're after. We're after a force, and this would be so I started with equation hunting, which is typical for students and is not necessarily wrong unless your goal is to not understand. Then it would be a wrong way to approach problem solving. But it's something that you're going to do, because you probably won't remember every equation. You'll have to look them up. And there's nothing wrong with being strategic and saying, okay, this is roundy. What are the roundy motion equations? I know I'm going to use one or more of them. You're guaranteed that. Since we're dealing with forces, you know you need centripetal acceleration. You must use centripetal acceleration in your force calculations if it's circular motion. And by the way, circular motion doesn't have to be a complete circular path. When you are on a turn in your car, those tend to be, there's some portion of that turn that is a circular path. Even if it's short, it just might be a short arc. It might just be a 90-degree turn, but that's a circular path. And you feel a force if you're going fast enough on a turn, you feel that nudge that pushes you out on that. All right. So this is other way to approach. So pretend we didn't do any of the blue stuff. Just rewind that in your head and say, the goal of the problem is force. We're dealing with circular motion, so I must need centripetal acceleration. Well, centripetal acceleration requires that you know the linear speed, because the formula says v squared. I'm given r, but I'm not given v. How do I calculate v? Well, I need omega to calculate v. So I don't have omega. But I do know that it goes one complete turn every 20 seconds. Poof, And you would be forced to do what we've already done. That would be another way you could start the problem. Some of you will naturally think that way, some of you won't. Hence, I want to point at the different ways you can go about solving it, because ultimately, you just need to get the right answer and done the thinking yourself. So now we have an opportunity. Well, F equals MA, so, oops, I don't need the highlighter with the pen. So F equals MA, but we're talking about the center-seeking force, which means we need the center-seeking acceleration. So you don't necessarily have to write those subscripts of C, but don't think that some other computation method for A will work. Like a delta V per delta T, that's not going to give you the right answer in a situation like this. Okay? So now I can just take the fact that the Nice was 42 kilograms. We just computed this right here, and so this is approximately 103.6 newtons. Capital N for newtons, and we have our value there. Now we're not done. We're just getting started with this. So I'm just trying to get some space here. This is a crowded desktop. All right. So any questions, I guess, about that? Fairly simple, maybe not obvious yet, but that will change in time, okay? So now what's going to be required for the rest of this? Well, let's use, so this is just the math version, but it told us that we want to calculate the total force, magnitude, and direction. Okay, we currently have part of the puzzle. This is just one aspect of the force on the Nice that's riding this. It's the part of the force that's keeping this cart in the Ferris wheel on that circular path. So the structure is bearing this force, much like this string, which is simpler than a Ferris wheel, is keeping that circular path going. So this is our low-budget Ferris wheel. What next? Okay, well, I'm gonna move things up here. It might pay to have a browser screen open with the other stuff, but let's use what we haven't done here is use some of the stuff that's at the beginning of, I forget which chapter I talk about system schema, but it's in there. And so a system schema is a way for us to pay attention to the forces that are acting on a system. And in this case, the system is going to be the Nice. Okay, so in a system schema, which you have reading and notes to take on, video and reading, you have some object. And so the Nice, she has some mass that's been given in the problem, 42 kilograms. And in a system schema, you just remove all of the clutter of detail in terms of size, shape, everything. And you just make a bubble and you give it a label that makes some sort of sense in your scheme. And the Nice, she's going to be this little M bubble because she's got mass. And if she's got mass and she's on Earth, that means that Earth is going to be providing a force through gravity on her mass. Well, we also know that the Ferris wheel that she's connected to in some way. And quite literally, the way we draw this connection is there's a contact force between her mass and the Ferris wheel. We just computed it. And so that C isn't for contact necessarily, though it could be. We're using that C for centripetal because of the acceleration. But in the system schema, the C is for contact. And then the Earth, in this case, doesn't have a contact force with her. We'll get to that later, because she's up in the air. But gravity doesn't care how far away you are. Eventually, gravity is going to connect with you and exert a force on the object. So this system schema is encoding for, so this is the Earth. This is the mass of the niece, okay? And those IE words, I before E except after C, or when sounding like neighbor or way, you'll always be wrong, no matter what you say, something like that. So the niece, if I spelled it wrong, oh well. So, and then the Ferris wheel. So this system schema, it lets us organize the objects that are in play. And the reason why it's called a system schema, a system in science, or especially in physics, is any collection of objects, one or more, all right? And so in one sense, our mega system, our macro level system, is the Earth and the Ferris wheel and the person. There's multiple things that are important here. But when it comes time to do a force calculation, in this course at least, we want to zero in on one object. And we call that our system. And so the niece is the object in our larger system of things that has forces acting on her. And we're concerned about her motion, the forces that she is experiencing. We don't care so much about the force that the Earth is experiencing, because she's also exerting a gravitational force on the Earth. In fact, they're equal. They're just opposite of one another. And what this system schema does is, once I pick the object that I'm concerned with, which is the person, now if I've accounted for all of the forces acting on that object, then I have basically set up my system schema, and the number of times that a force crosses or is connected to the object of interest, the system, now I know, there are two forces to account for. It wasn't just the force, the centripetal force, if you will, of the Ferris wheel acting on the niece. Gravity was also part of this puzzle, which we knew, but guess what? If you were a perfectly normal person, that totally flew out the window. You weren't thinking at all about how gravity was affecting her. Most people, all that math meant you just forgot about gravity. Well, you can't do that when we're summing forces. It's not allowed. And so in the book, I start with system schemas, and then we go from a system schema to a force diagram. And typically, physics textbooks just start with force diagrams as if it's perfectly clear to people how they work. And what we know from decades of research that is older than most of the people in a class like this is that people didn't catch that vibe on the way to using force diagrams. So some people decided, well, let's back up and come up with a way to fix this. So this is a modeling tool. It's an accounting device, if you will. Okay, well, what forces are at play here? And so now my force diagram must have two forces. in the force diagram. This isn't a force diagram. This is a system schema. A force diagram turns the system into a point particle. We're going to pretend that the niece is a point particle, all right? And we know that there's a downward force of gravity, which in the book, and I think you've seen this before, so I'm going to use a superscript. It's not an exponent. Force of gravity, and it's going to be the force of the Earth acting on the niece, which we've labeled M for mass, because we're dealing with her mass. You could have called it N. You could have called it ABC. It was whatever makes sense to you, because it's your model. It's not my model. It's your model. Using letters that refer to things by their name is usually better. So I know, and by the way, I could have written the system schema horizontally. The system schema is, you're not trying to position anything in the system schema. You just want to have every object sort of in orbit around the object of concern, so that you can draw these connections and account for them. All right. And the type of connection too. So we have two types so far. A contact force, C, which you can see right here, and then a gravitational force, G, which we label there. And in second semester, we have E for electric forces, etc. All right, so we have that. So we can check off the gravitational force that's below the person in our system schema, and this contact force, which in our case is also centripetal, so a little bit of symbol abuse there. So what did the problem tell me? Well, it told me we're going to calculate the total force on her when she is 1/4 revolution past the highest point. So that force, whether it's, it depends on what direction. So if she's coming around the top one way, we could draw that. So that would be there would be a force exerted a 1/4 turn past the high. So the high point would be here, and then a 1/4 turn. So there'd be a center-seeking force, and we could call that our contact force of the Ferris wheel on the mass. Okay? And so these are abstractions. They are abstractions that force us to slow down and think through things and account for them. And like any new tool, you have to use it for a while before its usefulness becomes readily apparent, unless it's a super simple tool. Hammers, relatively simple. If you hit the nail instead of your thumb, you realize how great they work. This is a little bit more complicated than that, though you might feel like banging your head on the desk. Don't do that. Not recommended. It is and then this labeling, these weird force labelings with a superscript and a 2-element arrowed subscript. So it's an object interaction. So it's a system object force interaction sort of system, where the superscript tells you what kind of force you're dealing with. The subscript tells you what is acting on what. And here's the thing that's important. You need the arrows in this notation to always point to the same thing. Otherwise, you've lost track of what it is you're paying attention to, because we're concerned with what's acting on the niece, which we've labeled with the letter M. So now I know, gravitational force of the Earth on the person, that's just mg. Okay? And this, the contact force of the Ferris wheel on the person, well, we just computed that. That's ma, but it's that special A, the centripetal. And so this is what's tough, because our alphabet only has 20-some letters. I was going to say 22, why I was thinking of Hebrew. 26 letters in English, I think, something like that. I've used it my whole life, but I think it's 26. Is it 26? I need coffee. Anyways, we just computed this. All right? and we'd ended up calling it F sub C above. So now we, in one sense, that the top part above the line was sort of us blindly equation hunting, which is, I'm not going to pretend that people won't do that. I know that students are going to do that even if I suggest that they not do it that way. So I want you to be able to at least be able to make some sense of that equation hunting. But now we're modeling. This is full-on system modeling using the system schema, from which I can use that system schema to verify that I've accounted for all the forces in my force diagram. And since there were two force interactions in the system schema with those blue highlights, that means I need two force arrows in my force diagram. And in the diagram, this is where I'm now starting to pay attention to how are things directed, because I'm using the standard XY Cartesian system, if you will. All right. And so, okay, what does this mean? So imagine yourself sitting in the seat. You are the niece. You are the person in this problem. You would feel two forces. You would feel like you always feel, whether you're paying attention to it or not, gravity's always pushing down. But you would feel, a force pulling you inward or outward. You would probably slide, but you're going to feel that force going, instead of going downward, it's going to be going, in or out, horizontal to you, parallel to the ground. Okay? So this picture is representing something you felt at least once in life. If you've been on a Ferris wheel, you've felt this picture. If you've been in a car on a turn, you've felt this picture essentially. Okay? Now how could I sort of move this picture towards the math a little bit more? So I'm going to kind of redraw this. So what do I have? There's a downward force of gravity. There's an out. Oh, it looks like I lost my. Like what happened to? I switched to eraser somehow. We have this outward force of centripetal acceleration, and that means there's a net force here. How do we know that? This is stuff we did week 1 or 2, vector addition, something you were supposed to be introduced to in your trig or pre-calc course, and then you were brought back to it again at the beginning of this course. If you add vectors graphically, tail to tip, that means the net force must be not exactly lined up with either force. It must be some angle between them, all right? And the angle we're going to be concerned with is this angle right here, okay? I think I've gotten down to the bottom of the page here, so I'm going to have to be careful how big I write. So this is a right triangle, which guess what? I get to do Pythagorean's theorem. So the net force, if it was Pythagoras, it'd be the F net, it's the hypotenuse, F net squared would equal FG squared plus FC squared, or, like we've seen plenty of times, if I take the square root of the sum of the squares, I'm going to get the magnitude of the net force. So we could have fooled ourselves into thinking that our first force calculation was the net force. The system schema says, oh no, you left one out. And so we move forward. So I'm not going to enter the numbers to do that, but FC we already know. FG has to be M times G, so it's going to be 42 times the gravity, 9.8. And so this works out to be about 424.4 newtons. In fact, I'll give you the numbers, we already know this is 103.6 newtons. This ends up being 411.6 newtons, if you did the math on that. You could go make your own Python trinket. I have a version that would do this computation, or the individual ones for you, but I haven't posted it yet. So now we have the question. So want to know the total force, magnitude, and direction. We just got the magnitude. Okay. This is the magnitude of the force. What about the direction of the force? Well, the direction of the force, hopefully this at least will look familiar. If you know x and y components, the inverse tangent of the y part over the x part, which means the y part up and down is gravity, the x part would have been the centripetal. If you do the inverse tangent of that ratio, whatever the y force is, or the sum of y forces ends up being, and the sum of x forces being, in this because the sums are just individual things, doesn't require that, then you're going to get 14.1 degrees. And it's going to be from the vertical. Okay? So that's what it took to answer this question. And of course, that's because I had to explain everything along the way. And so we could have cut the time in half or less if these things were already in your thinking. And so that's what we're here to develop, is that thinking from which you can do the math. Use modeling tools. Mathematics is one of the modeling tools, and get an answer. And so whether you're doing physics or not, that's what we do in science, all of the sciences, whether they're life sciences or hard sciences or even this what they call the soft sciences, social behavioral sciences. There's methods, and there's math, and there's a scientific progression that requires this same thinking. It just, whether we're talking about physics or chemistry or biology or psychology, doesn't really matter. And so to give you a little bit of a view, why do they make you take physics? And there's a number of reasons for that. Is forces and electricity underlie everything you do in biology or the life sciences, which is fundamentally biological. And so you need to have some knowledge of that. But physics is probably, it is special in the way that it approaches problem solving. I'm not going to say that your chemistry teachers aren't doing good problem solving. That's not what I'm saying. What I'm saying is physics is one of the oldest, if not the oldest, science. Chemistry and physics sort of came about together. They're kind of their own special things, two sides of the same coin, if you will. We do like to joke with the chemists, that it's just a branch of physics. And the only reason we get away with that is because physics is about moving things, and every other science has moving things in it. So we get to, that generalization lets us get away with that little cute little jab. And everybody knows that it's not entirely true in that regard. So the people that you are heading towards to finish your education, they want you to know some of the physics because it's relevant to the craft that you're in. So there's a direct connection. You really do need to know about forces and energy and electricity. And then we just want you to be good problem solvers in physics and mathematics. They help in that. So that's why. Those are the main reasons why. And how do I know that? Because I've talked to those people. Been in this long enough to have those connections and know what they're really after. And those are the general pieces of the puzzle. So that one problem, I think we spent about 30 minutes talking through that. And so hopefully that sort of opened your eyes a little bit. You may want to come back and just listen again and go, and start noting, why didn't you think that way? Is there a way that's more natural for you? And I would especially encourage you, either you're going to start in blue, like I did, or you would start in red, which would require you to do the blue. You could also have started with what's in black and realized that you need to go get centripetal acceleration. This you'd already have. You could have said, I'm just going to compute that force right now because I know I need it. But this centripetal acceleration, I'm going to need to know the linear speed. I don't know the linear speed. I need to get the angular speed. I have enough information for the angular speed. And it would go that way. So there's 3 ways that this problem could start. I started in blue, but you could have started in black, and that would probably be the best way because it's a force problem. Doesn't matter whether it's linear forces, circular forces, etc. And in fact, on your test, if forces are involved and energy, well, if it's forces, I want to see system schema. If it's energy, it's going to be energy pie charts, which we'll get to. I think you're taking notes on that next week. Or maybe this week, I can't remember which week it is. And that'll be required on the test because you'll take a test, you'll put in numeric answers, that's part of your grade. And then the notes that you upload are the other part of your grade. And so, yes, has system schema, has energy pie charts, has a force diagram, sums the forces. I'm looking for some things along that way. And so you could say, set it all up correctly with schemas and whatnot, get the wrong answer numerically, but if your setup was correct, that's half the points. And so I'm looking for process as much as your method as much as I'm looking for the right answer. So that's the way these tests will move forward. So if you do these things halfway right, you're going to get points. Even if you get the numbers wrong, we'll work on filling in those gaps as we move forward. All right. So that's problem number 1. This next one, a little bit easier. All right. While relaxing from studying physics, which is, important. Flipping through channels, see a circus show in which a woman drives a motorcycle around the inside of a vertical ring. You determine that she goes around at constant speed and that it takes her 4 seconds to get around when she's going her slowest. If she's going at the minimum speed for this stunt to work, the motorcycle is just barely touching the ring when she's upside down at the top, loop-de-loop. At that point, she's in free fall, so her acceleration is just g. She makes it around without falling off the ring. But what if she made a mistake and her motorcycle fell off at the top? How high up is C? Okay, so I've highlighted information and I've highlighted the goal. How high up is she going to be? Now, here, what do we want to do? So I'm going to start with forces this time. And the reason I picked this problem as not being a test problem is I'm going to use the problems as a way to build upon the other lecture content and reading content. And so the thing that's probably not obvious is that at this particular point, the net force is going to be equal to the centripetal force. All right? Sort of like back on our spring example, at that spot where she's just barely still on the track, okay? That would be a minimum So imagine she was slowing down to that magic speed so that she would then fall. That's where that centripetal force would be at a minimum, because as we go past that value, now she's no longer being held on the circular path. So if you come to the top of that loop and start to fall, that means that your acceleration wasn't enough to keep you on the radius of the path. And so what would be that radius? So the radius, when it's vertical, it's the height of the loop. All right. So, or it would be half of that, I guess, relative to the center. All right. So we can make this deduction, which admittedly is probably not obvious. But again, why would you, you'd have to think about physically what would this be like. So, probably none of us have done this stunt, which is why, we're still around, because we didn't try to do this crazy thing. But if you did, if you've probably ridden a bike and maybe you've ridden it up a hill, you sort of feel that force. Maybe you've done, if you've been a skateboarder, maybe you've done some of those curves and you feel this centripetal force. You've felt that. So just imagine, you would have to go, I think all of us know, you better be going the right speed. There's a minimum speed where this won't work, okay? And any speed above that, you're going to stay on the path. And it's faster speeds will keep you on that path. But eventually, if you slow down on that path, you're going to fall off that path at the top. You won't fall off on the bottom or the sides, but when you go around the top, if you're not going the right speed, you know you're going to fall off. So I think everybody knows that. So the trick here is why would I take this thing that's fairly obvious to everybody, whether they've taken physics or not? And why would we, now that we've been exposed to a bunch of physics, write that? And so I've tried to explain that. And if it wasn't clear, I'll just have you come back and watch the video again, or we can talk more in office hours or whatever. So here's a statement. The net force is going to equal this centripetal force. But what is, remember the net force, okay, what's the net force on the object? Okay, and again, just like in the last problem, gravity, all right? So we're going to have net force. These two forces must be in balance, okay? And I guess actually, let me, where's my eraser? Here it is. I want to erase that net, there we go. Let's make this a little bit more straightforward. At the top of that curve, right when she starts to come off the circular path, gravity and centripetal acceleration are in perfect balance. They wouldn't be in perfect balance when she's going faster. Okay? The centripetal force would be beating gravity. But there's a speed where they're the same. And below that speed is where the circular path stops being what this stunt person is enjoying. So now I have a math equation. I can go straight to some answers here. Now the nice thing here is mass, M-A-S-S, mass on both sides drops out, becomes irrelevant to this. And so all we have to do is go, okay, that means that I could solve for the radius, which is a height at that spot, and that's just going to be v squared over g. So problem is, I don't know her linear speed. Okay? Could have calculated it from the beginning like we did in the other problem, but I wanted to start this problem differently than the first problem because they're fundamentally the same problem. And so in problem one, I started with an equation hunting approach, and then did the forces, and this said, oh, okay, let's start with forces. Okay, I didn't draw the schema because I wanted to just explain the interaction and save some time too. So now I'm like, oh, I know, we want to know the radius. That's what we're after. So I have an equation that will give me radius if I know the other inputs. I only know one of the other inputs. I don't know V. And so what would V end up being? Okay, and let's see here. So let's sort of put a pin in that, if you will. We're gonna come back and use that in a minute. So I need V, and if I go back to my linear thinking, so I could write omega r, and I don't have, I could go that route. I'm not going to because we did it in the previous one. But we know first zeroth law would tell us that. So something super basic, like the most basic element of motion is this one. But what was that change in position, that path length, if you will? Well, it was a circle. It was 2 pi r. And that time was the period of circular motion. So I just took the idea of linear speed and I just put the path length of a circular, I just transformed it into something circular. This basic idea here, all right? And so what do I get? I get 2 pi r over 4 seconds, which means I have pi r over 2 meters per second. So all I did was provide myself with a way to substitute. So what's going to happen next, and this is why you took algebra, okay, is this V, okay, which we've just written this way, is what's going to go in here. So instead of leaving it as V, which I don't have an answer for, and even when I try to compute it, I get this pi r over 2, so basically half the circumference, if you will, because of the time part. So what we'll do is we'll come back to our computation. I'm going to switch colors. So r, but instead of v squared over g, I'm going to write pi r over 2 squared over g. Now I have r on both sides of the equal sign, but I have one unknown in this game here. So we'll write it all out. So I get a pi squared r squared over 4g. And so what this will boil down to is that when I cancel out one of those r's, if I rearrange it all, r is going to end up equaling 4g over pi squared. Those are all known values, and if you crunch the numbers, you get 3.97 meters, so roughly 4 meters. So 4 yards, 12 feet-ish, is how high she's up when that happens. So, sort of an interesting approach, something that's not entirely obvious, but it is simple. It's requiring simple facts that obtain from reading and thinking it through and things we've been trying to model and get into your head for the sake of this. So I'm going to stop here for today. And there's obviously 12 more pages or 12 more problems, because each page is a problem. So I gave you plenty of space to struggle with the math, if you will. It's up to you whether you want to take a swing at the rest of the problems, because we're going to pick up with problem 3 the next time that we meet and continue going through these motions and do as many problems as we can in these handouts over the next couple of weeks. So you have, I think this week you have some projectile motion testing to finish up and whatnot. And so I want you to be able to do those things. And so come to this later as opposed to sweating about it now. Also, the next one, the next problem, one of the reasons I'm stopping too is I do want to make sure that you're at least more fully acquainted with chapters 5 and 6. So that friction, because the next problem involves friction, and but we're going to get very good at doing force summing and whatnot. And like on this one, I can tell you, you have right now 4 of the remaining problems are test problems. 5 rather, maybe 6. We'll see what happens. And but we'll cover that when we get to it. Recording here. Let's start identifying some stuff. So, what are we supposed to do? We must determine a safe rate of rotation such that the stunt man will not fly off the merry-go-round and into the shark-infested pool. So here's this situation. James Bond film, there's supposedly the last of, what's his name, Daniel something. Gonna do his epic Bond thing, his last thing. And we have some information here. The diameter of the merry-go-round is 50 meters. Daniel Craig, that's right. Let's see. Coefficient of kinetic friction is 0.5. I'm going to ignore the static. We almost always do for this kind of problem. So that's the information I have. Okay. That's not a lot of information. So what are we going to do? So understanding the problem, if you will. So if something doesn't, and you've felt this, hopefully you can remember back to when you're a kid, you're on something that's spinning, merry-go-round. There's a speed where you're going to feel a pull off of that. You're going to get thrown off the merry-go-round, okay? When you take a corner fast in a car, you feel that push out to the edge. So what are we talking about? We're talking about that experience that pretty much everybody has had at this point in life. And if it's slow, you don't have to worry about it. You don't slip too much. And so we're trying to make sure that the force of friction keeps us in place. That's what would keep you in place. So if you, like in your car, if you had leather seats that you just armoralled, well, any curve will make you slide off the edge. But if you have velour seats and you're wearing corduroy pants and you charge it all up with static cling, it's going to be harder to move you. Okay, so friction is what we're trying to take advantage of. And this force that pushes you out is part of that centripetal force thing. And so what we are looking to do here is we want that centripetal force to be less than the force of friction. And if you've done the reading, the conventional symbol for friction is the lowercase f. So this is what we want to happen, all right? And what this means is that we want mv squared over r. So we've seen this a bunch of times now. We just did it twice in Python. It's in your notes that you've taken. It's in the reading that you've read, okay? This centripetal force thing, which is about the force associated with speed on a circular path. So if there's a force associated with speed on a circular path, you can just go mv squared over r. Get a t-shirt, get a tattoo. All right? Friction, again, it's going to be the coefficient of friction times the normal force. Again, that's from the reading, which is going to be, in this case, mu mg, because everything's flat. There's no sines or cosines. That will change for us as we move forward. And so, hopefully you notice that, this common mass goes away, and we would have v squared less than r mu, whoops, no m in there, rug, less than the rug, if you will, or mu gr, however you want to write it. That's great. I have no idea what v is. I don't have a statement about what v is. We were looking for that. How are we going to figure that out? We also don't typically talk about a roundy speed in terms of its linear amount. We usually talk about RPM, okay? And so there is an equation that would have been in the book where we know that speed, as related to angular frequency, would be, well, if we plug stuff in here, we would have this. So this is just putting those things together. So 2 pi r would be the circumference of a circle, and the frequency is how many times you go around that. So it's really a 1 over period sort of thing. It's an inverse seconds sort of thing. And so therefore, that's what the 3 little dots are. It's a little shorthand, a little mathematical shorthand. If I square that, because remember we're dealing with v squared. So if I square this, what am I going to get? I'm going to get 2 squared is 4, pi squared is pi squared, r squared, f squared, which would need to be less than this mu gr business. Okay, so I'm sort of merging, if you will, this business with that business. That's what we've done in that little piece of math. And you're thinking, oh my God, this math, what the heck? Okay, and so it's just math. Okay, let me go back to the beginning. Roundy, how do I not get thrown off the merry-go-roundy? Either I hold on really, really tight, I'm glued to it, or the friction interaction, meaning my feet on the surface, Daniel Craig's feet on the surface, whoever this is, Billy Crystal, etc. That interaction, which you've also studied in your notes and whatnot, is bigger than the force that's pushing it off. The force due to circular motion, that throwing out. Centrifugal, some people call that, okay? So I have this statement that says my v squared would be less than this product of things, friction, gravity, sort of, it's independent of mass. Mass keeps dropping out of these things, which is an interesting thing. So we have all that, and what we can do is, if you basically solve for the frequency, all right, frequencies will be less than, if I have a frequency, which we're going to turn into an RPM kind of thing, that's why we're doing it this way, would be the square root of mu g over 4 pi squared r. And if you plug and chug, and I'm not going to write that in, but mu, the kinetic friction, meaning the moving friction, 0.5, if you put 9.81 in there. And the reason why we would put 9.81 is that we're dealing with meters up here. So we would use the metric version. So that's another part of this science game, is what unit system are you in? That determines what the constant value will be, or because that's going to be associated with those length, time, whatever units are associated here. And so we get 0.88, what are called hertz. And you're thinking, all of this hurts my brain. Yes, I understand that. Hertz is just per second. That's all that means. Its units are literally 1 over seconds, or s to the minus 1. Sometimes a book would type that in. And so, we have this frequency. We tend to talk about frequencies in the units of hertz, which is how many times per second this cycle goes. So your stereo, you might be concerned with those frequencies, etc. Well, if you do frequency times 60, okay, that basically turns it into RPM. And so we have about 5 RPM here. Okay, now where does that come from? Good question, glad you asked. If you wanted to, if you took 0.88 hertz, okay, well, a hertz, or this unit, would be the same as revs per second. So I'm using this, often I find that chemistry students are familiar with this railroad track thing. I show it in chapter 0, I think, of the textbook. So I'm assuming that everyone remembers that perfectly well, right? And there's 60 seconds per minute. Well, the hertz units drop out, the seconds units drop out. So basically, what do I have? I have my hertz value times 60, or my frequency times 60 will give me RPMs. So I would recommend that maybe you kind of remember that. RPMs makes a whole lot more sense than hertz. Almost nobody uses that in their day-to-day life. Now in science, we use the heck out of it. But RPM is a way more natural. 5 revolutions per minute, 1, 2, 3, 4. That's, how fast or slow is that? Okay, so past this, I guess we have a problem. As long as it stays under 5 RPM, this works. So that's it for this problem. So the first 3 problems, the 2 I showed last week and this one, make it possible for you to do problem 4 on the celebration of knowledge, problem 5 on the celebration of knowledge, and problem 6 on the celebration of knowledge. But problem 7 might be a little bit of a stretch for that. So let's go over it. This is letting us apply all this stuff we've been reading about, some of what we've been modeling in the Python. So there's all these ways that we meet the course objectives and satisfy the powers that be who have defined how our courses, the things that need to get done during the semester. All right. So here's this situation, a Crocodile Dundee movie. If you've seen that, you remember the noisemaker the Aborigines had this thing on a string and it made some noise. That's how they communicated. And you decided you're going to make this, okay? And so we have a 400 gram noisemaker. On a 60 centimeter string, so that's going to be my R value, okay, inevitably. So it's got a circular path. This thing up here, this is going to be my mass. So hopefully, you heard in algebra class, make a list of values. Well, you could also just sort of annotate the word problem saying, okay, this is going to be the mass. And by the way, since it's in grams, we're going to have to make sure that we write kilograms because that's the SI unit for mass in, physics, all the sciences, quite honestly. All right. Swung with an acceleration constant magnitude of 20. Well, that means that this is my centripetal acceleration. So I think part of this is as you go through the problem statement, realize you're going to have to read it more than once, or at least read it slowly, taking note quite literally of what it is being given to you. And so swung in a circular path, because there's an R there, that means this is not just any acceleration, it's centripetal acceleration. Of course, we're also dealing with circular motion, so we would expect that there's always going to be a centripetal acceleration involved. And then you and your friends can agree where their maximum tension. So, hey, tension. Somebody mentioned tension. Let me get the maximum tension. I don't know. What is that going to be? And so here's the other thing. Last time we used the capital letter T, it was for period, a time for one complete revolution. But as you will see in pretty much every physics textbook in this galaxy, we will use capital T for tension when we're dealing with forces. So we'll use capital T for period, a time unit. We'll use capital T for tension in a string or a force when we're dealing with forces. We'll use capital T for temperature. In fact, you've already seen that if you've been in chemistry, like the ideal gas law, there's a T in there. Or the units of temperature will show up in those things, and we like to use T for that. So there's symbol abuse because we have a limited set of symbols. You have to, context defines what that means. Sort of like, I love my wife, I love cheeseburgers. Obviously, those are different loves. At least, hopefully, they are different loves. I would need counseling if they worked. And so this tension business, we're going to calculate the tension at the highest and the lowest point and compare them. All right? So this is the thing we want to know in the problem is tension. So if you're careful in the reading of a word problem, you can end up saving yourself some time in the doing of the word problem. Because every time you identify this is this and that is that, it frames your thinking and hopefully focuses it. So that's one strategy that you could deploy here. All right, so let's make a little sketch. So I'm going to do a looking down view of this noisemaker business, and put a kind of a center line through this, and out here, actually no, this isn't, I'm sorry, high and low point. I'm thinking of swinging a ball on a string. This problem isn't doing that. It's swinging it circular so that you're standing there looking at it from the horizontal, you see a circular path. Otherwise, you wouldn't have a high and low as the problem stated. So forgive me for that. So here we have this box And when it's at the top, okay, we would have a weight force down, or there would be a gravitational force down, and there would be a centripetal acceleration there. So I'm gonna get my colors coordinated here. So at the top, we have this. And then at the bottom, okay, still have gravity pushing it out, but the centripetal acceleration is still center seeking. So on the circular path, we need that centripetal acceleration pointing to the middle, all right? And because it's a center seeking acceleration. And then I guess we could have a, our circular path, something. It's a perfect circle. Just press the I believe button and marvel at Van Gilder's perfect circle there. All right. So, we could be going roundy in that direction. The radius doesn't change. It's ideally the circular path. So we've identified some values in the problem statement. We've drawn a picture. So on the test, I'm going to make some demands of you. One, I'm going to want you to, and now I'm not doing it on every one of these problems, but you've seen in lecture already last week and stuff you've taken notes on, the system schema. So I'm going to want you to draw a system schema. I've shown that in the book. I've shown that in some few examples. And I want to test you on your ability to draw a system schema. So I'm going to expect to see system schema diagrams because when you take the test, there's a number answer part and then there's your notes part, okay? So I want to see a system schema. Then I want to see a force diagram or an intermediate sketch like this one that gets to a force diagram. I've shown the force diagrams as well. This is sort of a mix of those two things, and that would probably be acceptable. And then I want to see your math. And so you'll get some amount of points for getting the number right on the online test, and then at the end of that test, you have a chance to upload a file. And I'll put all this in the instructions. And I want to look at your work. And if you do all the things I ask you to do, that I'll specify on the exam, then you'll get additional points for that work, even if you had work that was largely right but got the answer wrong for some reason, some computational error, etc. And so, and if you get them all right when you submit the exam online, then I guess you don't have anything to worry about. But if you don't get them all right, then I'll go in there and look and go, you had the right idea, here's another 20 points or whatever. And so there might be a delay if your numerical answers are right, but your process was right on any level. I'll be giving you extra points. So keep that in mind as we move forward. So, all right, so let's talk about the top. What's going on at the top in terms of forces, all right? So at the top of this thing, okay, there is a tension, and since things are center seeking on a circular path, we can define that direction to be the positive direction, okay? So that means the tension, and so if I do a force diagram of this, there's a tension and a weight, and I don't know what their relative sizes are. It's not as important. And if that's the plus direction, then that's the plus direction, okay? So that means that there's a tension force, which we decided to call T. We could have called it F sub T or whatever. Doesn't really matter. There is the weight force of the object, this 400-gram noisemaker object. And if I'm maintaining this circular path, it doesn't equal 0. It equals the mass times centripetal acceleration. So this is always the net force, Okay, so the net force is this sum of forces, and it's going to equal MA. So if you think back to the reading, net force equals MA. Okay, so let me put a little note here. Instead of that, I'm going to say sum of forces. So sum of forces equals MA. The particular forces are the tension and the weight. The particular MA, Newton's second law, is centripetal acceleration as your thing. This would also be the net force here. Okay, so I wish I hadn't used blue because that's my other force thing. All right, so now if I'm also going to put a tension at the high part. Okay, so top high, bottom low. I think that's the way the problem specified it, so we'll stick with that. So the tension at the high point would be this centripetal acceleration minus the weight. Common term is mass. It can factor out. And so if we do 400 grams, which is going to be 0.4 kilograms, okay? 400 grams would be 0.4, divide that by 1,000, move the decimal over 1, 2, 3. The centripetal acceleration was 20. Gravity's 9.8. That means the tension at the high point is going to be roughly 4.1 newtons, approximately 4.1 newtons. Okay? So that's what's going on at the top. At the low point, what do we have? And remember, so tension is going to be in the string kind of headed that direction. All right? So the tension at the low point, okay, so that tension is going to be going up on our diagram, okay, so that's one force. The weight is going to be going down at the low point of the swing of this noisemaker. And that sum of forces, the net force, has to equal MAC again. So notice the difference. At the high point, we have tension, weight, centripetal acceleration. And at the low point, we have tension, weight, and centripetal acceleration, but the relationships are different. Okay? And that shouldn't be surprising to us, given what we drew in the picture. So the modeling game here, an important scientific skill. So T low will end up being MAC plus the weight. So I want to pause here to say, let's think about this. When it's up high, it's a difference, and when it's down low, it's a sum. Okay? So at the top, you're kind of easing that tension, but at the bottom, it's pushing down more. So it sort of makes some physical sense if you stop and think about it. Maybe you can go outside and try it later, or inside if you are confident you won't break anything. All right, so now it's the same deal. Mass pops out, and so if you plug and chug the same values as before, you get 11.9 newtons at the low end. Okay? Now, we just that's the answer at the low point. We gave the answer at the high point, and now we need to compare them. And so what will comparing them lead to? Well, we could just say, well, the ratio, T low to T high, if I do 11.9 over 4.1, then I'll get roughly 2.9. So the low tension is about 3 times the high tension, or 2.9, whatever, if you want to be specific. So it's a comparison. And hopefully the string is tough enough. It appears that it is when we do that. So that's applying all this force stuff to a real problem. You could go do this. You could put a ball on a string, could put anything on a string, and this would be the thing. In fact, if you filmed it, you could figure out what the actual centripetal acceleration was. Okay? If you knew how long the string was, you would know. You could do this problem using video analysis. I dare you. I triple dog dare somebody to do that. That would be a great lab. You're not required to do it, but you could. All right? And then you could do the math here, except with different numbers. The string length is different, the weight is different, or the mass is different, and inevitably the acceleration is different. And you could prove that point, if you will. So, any questions on that problem? All right, number 8. Is on the celebration of knowledge. Basically, it's the same stuff as what preceded it directly. All of it, really. And again, I would recommend that, so hopefully if you did what I asked, which was do your video notes due, I think last night or today, then you don't have anything to do this week. You finished week 7, and now that you know that next week you're going to take a test, and you're going to begin to take a test in this stuff, then maybe you would start working on that, and if you run into trouble, you would contact me or get in a study group. I'll probably put, I'll tell you what I'll do. I'll make an assignment to where you turn in your work for this, which means there'll be a conversation thread that goes with it, et cetera, so more easy points. All right. And then the work will be fundamentally the same on the test, except for the numbers. So here we have another situation. This is kind of related to the Earth orbit Python lab. So let's take a look at this. The satellite will be in a circular orbit 200 miles above the surface of the Earth. So we have a radius. I keep wanting it to be a different color. There we go. So we have radius. We've identified a radius. Then we have another radius. Okay, well then, I guess maybe we'll call this, boy, this pen color's not cooperating. We'll call this radius of the Earth. In fact, let's do something a bit more natural. Instead of calling the radius of orbit R, let's call this the height above the Earth, because that's the way we would talk. That thing is some height above the Earth, and then the radius of the Earth will be this little RE. We'll just call it that for now. So really, from as far as Newtonian gravity is concerned, we're talking center of mass of the Earth, through its mass and along a straight line, through the crust, through the atmosphere, at that height above the Earth to where the satellite is. So this is ultimately going to be our big R in an equation like V equals omega R. So instead of omega big R, we're going to have the radius of the Earth plus the height of the satellite. So I chose my letters for that particular reason, because I have this general equation that talks about speed of an object tangent to a circular path. So v is the speed tangent to a circular path, or at a right angle to the radius that defines that circular path. So again, when you see these equations, it's fine if you know them or can memorize them, but what you want to do is understand them. And understanding for human beings tends to come in the form of some sort of language, like words that we write or speak, pictures. Those are ways that we obtain understanding, and that's hard work, especially in science, which is why physics is required for lots of science majors even that aren't physics, is because physics has a way of really pushing that envelope. All right, so we have this equation here. We know that centripetal acceleration is that v squared over r, which means we're going to have v squared over, in our case, r is re plus h, okay? And so this works out to be omega squared re plus h, all right? So we have a version of centripetal acceleration, and we're wanting to find out, I think, how many times this passes the spot per day, given that stuff. So here we just sort of did the circular motion modeling. We didn't answer any question. So one of the things that makes it hard for students to learn this stuff is that they approach these problems like you were taught in math class, which was equation hunt until you got an answer, or apply a rule blindly because that's what the rule says. Here we have to do some modeling at the beginning so that we get our bearings on this problem. What do I need to know that I don't know? What math equations am I going to use, not use, etc. All right. That's sort of the circular motion part. And then I think, too, you look at the heading on this thing, force and circular motion. So you're going to have to think about circular motion, and you're going to have to think about force, and then you're going to put them together. So if you want a template, do that template. Model the circular motion part, say something about the forces part, and then bring it together. Okay? So now let's talk about forces. So this device, so there's some sum of forces on the device. And basically, the sum of those forces are zero. That's essentially why it stays on the path. And so that means if you were doing a system schema and then a force diagram using that interaction notation, you would have the force of gravity of the Earth on the device, and that needs to equal the centripetal force, okay, which we'll just call F sub c since we've used that prior. So what does that mean? So this, I showed this earlier when we were doing the Earth orbit code, where I showed mv squared over r equals Newton's law of gravity. So here you have Newton's law, which we've seen a couple of times now, Newton's law of gravity, okay? And instead of over r squared, since our r is the radius of the Earth plus the height of the satellite above ground squared. That's the total distance over which gravity is acting. This would equal what we showed above. Instead of MA, RA, our acceleration will be omega squared RE plus H. All right. Well, yay, the little mass of the device ends up being completely irrelevant. We're wanting to know this angular frequency or angular speed. That is the goal of this problem. And so if you do all that rearranging, you'll get that big GM on top, that radius thing in parentheses, that'll come down and increase the exponent from 2 to 3. So we'll have a cubed thing in there. And so if we, I'll go ahead and put some values in here, I think. So 6.67 times 10 to the minus 11th, there's a bunch of units on that, which you took notes on. Instead of 6, it's 5.97 times 10 to the 24th kilograms, like shown above, so these values are up there. Now, the radius of the Earth, it said it was 6.38 times 10 to the third kilometers, which would be 638,000. How many get kilometers to meters? Okay, so you could just Google that, quite honestly. I highly recommend. Like if you wanted to convert meters per second to miles per hour, which you need to do several times, I highly recommend that you not do it by hand. Just go to Google and say 12 meters m/s to mph. Poof, it'll just tell you. Give it a whirl. It's really great stuff. So there's going to be some stuff here converting that. And then the height above Earth. And does it tell you? 1 mile equals 1,609 meters. So I could say 200, whoops, that's not multiplied. That's added to 200 miles, which if I multiply by 1609, I'll get the number of meters. You could also, like I said, Google 200 miles to meters. It'll give you some number, and you would put something other than a product in here. Anyways, if you go through all of that input, you're going to get roughly 1.15 times 10 to the minus third radians per second. And hopefully you remember this is the way. Sometimes the way of the Mandalorian is the hard way. And in physics it is. Nobody uses radians per second in their everyday life. Nobody. But everyday life isn't science life. Science is that kind of thing. And in order for the math to work out nicely, we need to do the math so that it has essentially no unit but time, because radians is really just an angular measure. It's not a unit in the same way that other things are units. And if I multiply this, so this is free knowledge, if you multiply this times 60 over 2 pi, that'll give you RPMs. You can do that conversion if you want. I'll show that here in a second. And so that means omega would basically be about 1/100th of an RPM. Okay? And that's going to be about 14 times in a day. So, why would that 1/100th of a revolution per minute? Okay. So let's do our little reality check. Here is the speed that this happens at. Now the question didn't ask for this reality check, but I'm going to give it to you anyways. So if I do this math, to this angular frequency. So you think about it. This angular frequency, this is a really small angular frequency. Because 10 to the minus 3 means 1/1000th. So this is a really small number of radians per second. Like 1 radian is like 57 degrees or something like that, if you do the conversion. Well, seconds, if I want to get to miles per hour, which is what we're most familiar with, there's 3,600 seconds in an hour, and there are the number of miles that we're talking about now. This is going to seem like it comes out of nowhere. You would have to convert the radius of the Earth plus the height above the Earth to get this 4,164 miles. Okay, so I'm not gonna. I'm telling you where that comes from, but so now I have. Note that radians, that's not a unit. That means number, but we use it anyway. So that means that the speed of this thing is roughly 17,000 miles per hour. And guess what? We can get a satellite to do that. That's kind of typical. It's hard to get things to go much faster than that and have them not break apart, but we do have things that go faster, but not much faster. So this problem here, we can put a fork in it and say it's done. Let's see, how's our time? I need to get through all of these here. So number 10, so I'm going to give you some things first, and then we'll little m, you need to think about it two-way, mass of sun or mass of a normal star. So in this problem, we're going to think about our solar system and then extrapolate that out to others. So sort of have some notes here. We'll call big M the mass of a neutron star, because a neutron star, even though they're smaller physically than other stars, they're just, how do they cram all that gram? They're just really high density and have often hundreds to thousands, millions of times more mass than a regular star. Okay, so we'll give it the big M because its mass is going to be much larger typically. We'll call our R, just big R, we'll call it radius of Earth orbit. And we'll call T the period of an Earth orbit. So in this situation, we're reading about pulsars, which are neutron stars that rotate really, really fast, like millions of miles per hour speed rotation. And here's this period of rotation of 4.8 hours. Astronomical object emitting these signals. So when they do that, because they're electromagnetic things, stars are electromagnetic, all of them, even our sun. That hence you've heard of these magnetic storms from all of these particles that it spits out every now and then, solar flares, etc. All right. So we're just going through all this. So this pulsar is a normal star. This is a theory, so we're kind of testing this theory. The period of that signal, okay, is the period of the orbit. The distance between normal star and neutron about the same as it is between Earth and Sun, so this is why we're making these notes here. And if this theory is correct, you realize, hey, I could do ratios and figure out how much more massive something is. Okay, so it's a detailed problem. This is why I'm not putting it on a test. I'm using it as a way to do the math. Okay. And so some of these problems are just so that you see how this math comes together. Some of them are much simpler so that you can actually copy that and do the math. So there's the secret sauce is out. All right, so concerning this orbit, I know that the force of gravity needs to equal this centripetal force, and that means one more time that G little m big M over an R squared has to equal a little m V squared over R. This is about the sixth time we've done this, okay? Which isn't surprising in a force, orbit, circular motion sort of thing. And so that means the thing that I showed you at the beginning of today's activities, this is what boils down out of that. The speed that is required to maintain that circular orbit, which is defined by the radius, R, that's the relationship. The big mass is known, G is a constant, R, I believe is known, or we have to, we're gonna get rid of R because we don't know that, if I remember, memory serves me well. So let me put a note on here. This is the speed to maintain orbit at R, circular orbit at R. Just a little note, I gotta keep re-emphasizing what does this equation mean because we keep using it. All right, so we know that V, let me switch colors here. This linear speed is also the path length, and the path length of an orbit is the length of a circle or the circumference of a circle over time. This is just average speed, distance over time. The distance is circular path, the time is the period one complete circular path orbit. This is an amazingly simple formula that was in math courses that preceded this course. And no rocket surgery here, even though it might deal with rockets, but that is another way to talk about the speed along this path, the length of the path divided by the time that it takes to go that distance, okay? But it also happens to be equal, like we just found with the force analysis, to this square root of Gm over R. Well, how do you get rid of that square root? Well, we would have to square both sides, okay? So now I'm gonna get 4 pi squared R squared over T squared equals Gm over R. So now I don't have any irritating square roots to deal with. And what this gets us to, if you solve for mass, we get 4 pi squared R cubed over GT squared. Okay, lots of stuff to plug and chug here. So let's go ahead and go through it. Well, 4 pi squared, that just is what it is. R cubed. Well, you would have to go look up the distance, and remember we're comparing this other star system to our own, okay? And it just happens to be the case, if you went and looked up this R that we called the radius of the Earth orbit, you've heard that the Earth is 93 million miles away, okay? But we don't deal with miles. In physics, we deal with meters. So we're going to be cubing that length. G is 6.67 times 10 to the minus 11th. And I'm going to go ahead and use the units here. These are Newton meters squared per kilogram squared. That all shakes out nicely for us. We don't really need it. And then the period of orbit, and here's this 31,500,000 556,952 seconds. And that gets squared. If you went to Google and you said 1 year equals, or 1y to s, it would tell you this answer. And so this will be approximately 2 times 10 to the 30th kilograms. If you plug and chug all that on a calculator, and you might want to, instead of using your handheld calculators, because historically, when it gets this many things piled into one computation, lots of us, myself included, will fat finger that calculator, and something will get entered wrong or parenthesis out of order. You can go to Mathway and actually type this in and look at it and go, okay, yeah, I typed that in correctly, and it'll spit out an answer for you. It won't handle units, but it'll do all the number crunching for you. And so what's the ratio? Well, this big M to little m, 2 times 10 to the 30th to basically 6 times 10 to the 24th, that's roughly 335,331 times bigger. There we go. Now we know. And the math was simple. I mean, literally, you're thinking, that doesn't look simple, it looks too difficult, but let's be for real here. This is not difficult. If it's maintaining a circular orbit, we know those two forces equal each other. Solving for that's just algebra. In fact, it's not even college algebra. It's beginning algebra. That's not intermediate algebra. This bit of knowledge that gets us into the land where we can get a solution, also not complicated. Why would you think of it on your own? That might be more difficult because we are at the introductory level of mathematics and science. Just think about where we're at in space and time as students, or where you're at. Everything is the introductory level at the freshman, sophomore level. Everything, all of your math, all of your science, English, you name it, psychology, all that. It's all introductory level stuff, meaning here's a bunch of tools. These are the way we use these tools. And then as you move on into your specialty, you push certain tools aside, hold on to the rest. That's what we're doing here. Now, the rest of this, this gets a bit tedious, but it's just introductory algebra. Plugging and chugging all of this, that could get gnarly. But the problem isn't that you're not smart enough to do it. The problem is data entry. That's where that goes wrong. You put in the wrong number. You type the wrong. You put a square instead of a cube. Those aren't. It's not because you're not smart. You're just not careful. In fact, I would say most errors at this level of whatever, it's careless error more than it is fundamentally, conceptually wrong things. But that happens too. All right. So that one. Now this next one, how's our time? We should be good to get this one out. Sort of need to make sure we get this one out because 12 is on the test and it sort of needs to, I think what I'm going to do is I'll end with this one, but I'll upload, we'll see how our time goes. Upload the other one, but this one, you sort of need this one to do 12 as I recall. So a plane. Okay, so I want to, here's a situation, we're talking about a plane that weighs a certain amount, and by the way, this right here would be 100 times 10 to the third, so a little typo there. It's not 10 times 103, it's 10 to the third pounds. That's what that's supposed to be. So in this thing, level flying, you get a certain kind of lift, and then when you take a turn, lift still happens, but it's going to put different forces on the whole plane and the wings. So we need to work that out. So with level flight, okay, what you're going to have, so if I turn the plane into a point particle, it makes it easier to do math. It's going to have a weight, mg, which is what we're dealing with here. And there's going to be a lift force, which sometimes is labeled with just the letter L, on for level flight. So it's a really simple force balance. It's the lift force equals the weight, okay, when it's level flight, okay? But when it's not level flight, all right, it's going to be a little bit more complicated. So let's look at the banking viewpoint. All right. So you're going to have, so we'll make the plane, we'll still make the plane the dot there, but then, so we're tilting the plane, okay? So I'm gonna put some XY reference on this, so call that Y, plus Y and plus X, if you will, just for reference. And so the plane's weight will always go down towards the surface of the Earth, towards the center of the Earth. But now the lift force is perpendicular to the wings, okay? It's lifting it up. And so there's some angle that's deflected at, and so the lift force takes on some different, the interaction is different. And so I've drawn a force diagram of this here, and I can see these two things here. Now, I also think it's going to be important to look at the banking from the top, because it says in the problem that require that it be able to turn a radius of 2 miles at constant speed of 500 miles per hour. Okay, so let's do a top view, because that's how I'm going to see the circular motion. All right, so I have to marry up the idea of circular motion, which I can visualize from a top or up view, because that's where I see the circle. I don't see, if I'm looking at the plane as it's turning, I don't see its circle. Okay, so I need to think about its circle, if you will. So here's the plane again as a dot. And here's this 2 mile and this is a perfect circle, by the way. Okay. So at 2 miles out, this radius, if you will, and it's going to be going a linear speed. So we don't talk about the circular speed of a plane. At the throttle, it's looking at how many miles per hour or knots usually. Probably is what's there in the cockpit, I don't know. So this is sort of the top view with our knowledge imposed onto the diagram, if you will. So now I have to bring those two things together, all right? And what I'm gonna have, so I'm gonna bring it up here so I have some, because I think I'm running out of space on the bottom. So I'm gonna draw let me kind of section off my panel here. So I'm going to put the plane there. I'm going to kind of give its wings a place. I'm going to bring these ideas together into a 2D force diagram. version here. So what we're going to have, let me do that. So in an XY, I'm going to have this lift force, but this lift force is going to be at the cosine of that angle because it's adjacent to the angle of our pitch, if you will. The weight force still points straight down, and then there is this mv squared per r thing, which happens to equal the lift in the sine direction. All right, so that's our, I guess, our mixed view. And just for humor's sake, I'll go ahead and say mixed up viewpoint because I know that some of you are thinking that. So I won't pretend that it's not there, but let's have a little fun with it. All right, so now I have a force diagram. If you can get to a force diagram, that means you can do sum of forces and get an answer. All right, and so that's what we're going to do. So if I sum the x forces, all right, I'm going to do that. This means that my horizontal, the only horizontal force, which was some fraction of the lift force, and it's a fraction of the lift force, and so think two things. Sine, cosine, tangent are fractions of something. And so the lift force, it's a fraction of that lift force because I tilted it away from horizontal. I made a triangle. Therefore, sine, cosine, tangent, those are going to be ways that I account for that fractioning of whatever it is, in this case of force. And that's going to be mv squared over r. All right? So that means the lift force is just going to be mv squared over r sine theta. All right, so I have that. The sum of y forces. Here again, in the vertical direction, I have something in balance because we're assuming that when it banks the plane, it stays, there's no motion in the y direction. Just tilts it, stays on that circular path at the right height above ground. So now I'm going to have the other thing, the lift force and the cosine thing equals mg. So now the lift force equals mg over cosine theta. And so, okay, lift force equals lift force. So these two things would come together, all right? And the masses are going to drop out. So you have v squared over r sine theta equals g over cosine theta. And that's going to give me the tangent of theta equals v squared over rg. And so what does that mean? That means I can find the angle that we're going to do this with. And so if you do the inverse tangent of all that, so inverse tangent of, and you would want to put, since it's going to be, we have 500 miles per hour, so we'd have to convert miles per hour into at least feet per second. So it'd be some number of feet per second. The 2 miles would have to go to feet. G would have to go to 32.2 feet per second. Okay, so I'm not going to do all of that, but this is going to give us 57.7 degrees. That's what this pitch is. That's almost 60 degrees from the horizontal. And that means, once I know that, I could take either one of the lift equations, plug the value in, so like mg over cosine theta, that's the simplest one. So mg over cosine of 57.7. Mg was 100,000 pounds, if you will. And so, or you could just realize that 1 over whatever cosine of 57.7 is, which happens 1 over that is 1.87 mg. So you could just say, because if you look up here, mg, I don't really need to crunch that number. Could you? Yes, you could totally crunch that number and then go, is this going to work? And according to this problem, we need to make sure that we don't violate this 4 times the weight. And so we don't. It's under 2 times the weight. So the plane won't break and everybody goes home safe. All right. And again, admittedly, I don't expect that these problems will make perfect sense after I'm done talking about them. This takes contemplation, takes thinking about it. It takes probably asking some questions about it. All right. And so let me be clear about that expectation. I don't expect people to go, oh, obviously what he said makes perfect sense and now I get it all and I don't need any more help. I don't expect that. I have you take problem notes on other problems in the video. I'm having you do that now. And you should have way more than you need to answer the other questions. The other questions are easier than the ones I'm showing. And their parts are all factor into the ones that you're going to be tested on. And so I'm going to want you to try those things and wrestle with it and wrestle with me as well. So this one will be on the subject of knowledge. Last problem, we should be able to get this out and call it good. So I'm going to, I want you to just take a moment to read that problem while I draw the force diagram. All right, so I'm going to start talking as I label this. So this angle, and I do explain some of this in the book, or at least I show it. Similar triangles let me know that the angle of the ramp ends up being these same angles in these locations. So there was some trigonometry you were supposed to learn in prior courses. So the N, big N, sometimes it's little n, the normal force, meaning the surface reaction force. So if you put something on a table, the weight of that thing is pushing down in the table's pushing up, otherwise it would fall through or bounce off. It's called the normal force. Read about it in the book, talked about it in lectures, so this shouldn't be a new idea. Since the vertical, and again, this plane got tilted, so we have to do one of two things. Either talk about the tilted forces in terms of traditional XY axis, or talk about the rotate it all. So in the book for an inclined plane, I rotate it all. This is a banking car. And so I'm not going to treat it the same as the inclined plane because the motion is not up and down the inclined plane. It's easier if we just talk about things relative to the standard XY plane. So that's a subtle difference that I want to do. But if it's parallel to the angle or adjacent to the angle, it's a cosine. If it's the other way, then it's going to be a sine. So the components of the normal force, which is normally on flat ground, normal force equals weight, mg. Now it's going to be mg sine or cosine theta. Okay, so this is the first time we've done that. And then this friction force has a component now that's downward. And so this would be an F sine theta. Okay, and there we go. So here's our force diagram. And if we sum the y forces, okay, which are going to be 0, then that means this n cosine theta is going to equal the sum of the down forces, which is going to be weight plus F sine theta. All right. So I'm going to n cosine theta minus mu n sine theta because F, friction, is defined as mu n, the coefficient of friction times the normal force. That's its general definition. Again, you've had a chance to deal with that in the book. So that means n would just be, in this case, mg over the rest. Mu sine, that's a really terrible mu sine theta. Let me write that better. I'll write it betterly. Don't tell the English teacher I said that. All right. So that's our normal force. Yay, we have this big ugly definition of the normal force. That will pay off later. What about the x forces? And so as I've shown in other lectures and in my book, we're always summing x and y forces, which means we need a force diagram that's keyed to x and y forces, et cetera, et cetera. So this means that I will have n sine theta equals mv squared over r. And so, all right, n can pop into here. And so what do I get? I'll get mg sine theta over cosine theta minus mu sine theta. And that's going to equal mv squared over r. The m's drop out. Okay. Math, 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 math. So you get this big ugly velocity thing. And if you plug and chug all this stuff, so let's take a moment to deal with that. All right, so according to the problem, the radius of the circle is 1/2 mile. Okay, I'm gonna do everything in feet. So 5,280 feet, half of it, 1/2 mile. Since I chose feet as the unit, that means I'm going to have 32.2 feet per second squared. So I'm using the English system, or I think it might be called imperial. The angle of this bank was a whopping 4 degrees. So down here in the bottom, cosine of 4 degrees minus mu. Which mu? It's moving, so we're going to use kinetic, which was 0.8 according to the problem. And it's going to be the sine of 4 degrees. So while that's a bit tedious, there's nothing super complicated about that. And you get 79.4 feet per second, which if you went to Google and said 79.4 feet per second to mph, you would get 54 miles per hour. Doing that mainly because that's a reality check. Can you go 55 miles an hour on a curve? Yeah, if it's not too banked a curve or not banked enough, you could go 54 miles an hour on a curve. If it was flat and a turn like that, you might not want to do that, but if it's banked a little bit, then you probably aren't going to slide off the road because the forces have been tilted a little bit. All right, so I'll end that there. That's the end of, oh, we do have one more. Problem 14, and we have time. Forgot about problem 14. This one's a bit simpler, and this will help you on some of the other problems. So here's this, it's one of those carnival rides where you sit in a chair and they swing you round and round, okay? So again, while you're reading that, I'm going to draw the picture. All right, so the diagram on the left, force diagram on the right, or picture or sketch on the left. So a chain, I think it is, with length of 30 feet at some angle that I don't think we know. And that's going to be a problem that we have to get rid of. Now, if you think down here to blue, why is R equal to L sine theta? Well, it's the trig. This R is opposite the angle, so just sine is opposite R over L, so that means I could write R as L sine theta. So we expect that you remember that from your trig classes. So once again, if I sum the y forces, which are going to be 0, that means I have a t cosine theta equals the weight. I'm going to call just big W. Now you saw that for work in some of the reading and whatnot, but we're going to call it big weight because that's what a lot of textbooks will do. So he weighs 200 pounds. Is this safe for a 50-pound child? So that is ultimately the question that we're after. All right. So I'm just going to use that for now. And the sum, big sigma there, the Greek symbol for summing, for the x forces is going to be MAC, because think about it horizontally. If you're looking down, you see that circular path, all right? And so what do we have for that? Well, now it's going to be the sum of forces, going to be T sine theta, the up force. And so realize, what do you have? You have tension in the rope and you have weight force down. That means you just have two forces in balance, but since it's tilted, you have a fraction of that force in balance with the other one that's not tilted. So just thinking through it, what should I expect? And this is going to be mv squared over r. Okay, so now we've summed the x and y forces here, and we have two equations with a common term, all right? But I'm going to take this and run with it. T sine theta. Now, instead of using v squared, okay, we know that that is would be omega r, if you remember that equation. And so now I have m omega squared r, and that's in the textbook as well. So I'm going to put, and r is L sine theta. So that means I could have m omega squared L sine theta. There are some nice things about this. For one, I don't need the sine theta anymore. Same on both sides. Up here, I can write let's get to this. So T, the mass. How am I going to do this? Well, it's going to be the weight of something divided by gravity. Now, here's the thing. Some of these problems, when they say somebody weighs 200 pounds, are we talking about the force or are we talking about the mass? Because for some imponderable reason other than history, here in America, in the West, people that use the pounds to describe the weight of something, often pounds force equals pounds mass, but that's wrong in physics terms. It's sloppy, it's confusing, and it leads to confusion in places like this, because the way this problem is stated, it's not clear that we're making a differentiation, except he weighs 200 pounds. So we're going to assume that the 50 is talking about the weight of a child, and if I use the word weight in a physics class, I'm talking about a force interaction. And that means if F equals ma and weight is the force we're talking about, then that means mass is weight over g. That's not obvious. I don't think that's obvious. And we don't spend very much time in textbooks making that, because we spend it all in the metric system. And newsflash, we live in America, which isn't on the metric system, but ought to be. And so you have to be able to be fluent between those two systems. Hence, I try to have some problems that force us to do that, so that this skill is at least marginally transferable to your real life in the future. And that's easier to say than do. All right. Omega is going to be 2 pi over the period. Again, that's just a general definition that predates this course, but we use it, it's getting squared. And then the length. So now I believe I have a force equation, or tension of the rope equation, chain that we're concerned with, all in things that are known. So if I put the child, which has a 50-pound weight, and since we're dealing with pounds, then it's 32.2 is the constant for gravity instead of 9.8. 2 pi squared is going to be 4, or the quantity 2 pi squared will be 4 pi squared. The period was, I think, 3 seconds. Yes. Once around the tower every 3 seconds, so 3 squared is going to be 9. I'm leaving the units out. And the length was 30 feet, so I can just use 30 since it was all feet. And so that means we're going to have 204.3 pounds of force. This problem is here for two reasons. One, it's a relatively simple application of these force laws for circular motion that allows us to use some trig, like the radius of the circular path is related to the length. And it also forces us to deal with this little nuance about, am I talking about weight or mass when I'm in the English system, because we often will say, oh, 200 pounds mass is the same as 200 pounds force, which is stupid, but we do it, and we'll never fix it probably, unless, I don't know, And so therefore, since this is greater than the 200 pounds, it's not safe. That would be the answer to the question. T greater than 200 pounds.